Well, there's so much more to DGX-1. The thing that is important isn't just the fact that we built something super fast, something super cool, but the architecture of it has to enable new types of applications. And one of my heroes, somebody who, before anybody talked about deep learning, before anybody else was talking about the importance of this new computing model, a researcher was explaining all of this to me in languages that I understood, explaining to me the impact of this work. Bryan Catanzaro, where are you? Where's Bryan? Bryan Catanzaro is researcher at Baidu. He was formerly one of NVIDIA's greatest researchers. He was one of the reasons why NVIDIA got into this whole business in the first place. And you're my hero. I just want to tell you that. I hope it doesn't embarrass you. And
well, I am thoroughly embarrassed at this point.
not only are you graceful, gracious, and just an utterly brilliant researcher. Very few people in the world knows as much about deep learning and the intersection of deep learning and GPUs, because he knows so much about GPUs. And today I invited Bryan to come and share with you some of the research that he's doing. And would you like a little clicker?
Sure. Thanks.
Bryan's going to tell you about just a little bit about the work that he's doing on Pascal.
Great. So at Baidu, we're really excited about being able to use Pascal and NVLink to accelerate the training of our recurrent neural networks. And I wanted to mention a little bit about what a recurrent neural network is. So convolutional neural networks are often used for processing images and video. At Baidu, we care a lot about sequential data, text, and speech. And I think these are really useful for many different kinds of AI problems. Recurrent neural networks have a time series dependence. They operate on time series data, and then they produce a time series output. So for example, in speech recognition, we operate on an input waveform that's sequential samples taken as time goes on, and then we produce a sequence of characters that represents what the user said. So this sequential dependence is the power of RNN because it gives it memory and it gives it the ability to understand the dependencies in the data, which are very interesting. But it also makes the parallelization of the training process more difficult. There are two major ways of parallelizing the neural network training process. One of them we call model parallelism, is basically where you take a look at your model and you realize, wow, there's so many neurons here, I could partition them and assign them to different processors. Say, for example, I'll put half of them on GPU 0 and half of them on GPU number 1. And then the other kind of parallelism is called data parallelism, where we realize, hey, our training set is huge. It has thousands and thousands of hours of audio data, for example. I bet we could chop that up in pieces and then assign different pieces to different processors. We have been trying to use model parallelism for many years, on and off, for different applications, and it's always been difficult because of several things, one of them being the interconnect between processors. And so Pascal is going to really help out in that regard. Not only is each GPU much bigger and much faster, which we really need, but the interconnect between GPUs is much better and has it's faster, and it also has new capabilities that we're going to use for interesting things. And I wanted to give you sort of a sneak peek at some of the things that we're thinking about doing with these new capabilities. We've been working on a project for a while called persistent RNNs. And the idea behind persistent RNNs is that since the weights are reused over multiple time steps as the model iterates sequentially over the data, we can actually keep those on chip, keep those persistent in the register file of the chip, and then do all of the math without needing to talk to memory nearly as much. And the advantage of this is that we can reduce the number of training examples that are required to keep our GPU busy. So instead of needing 64 examples to keep the GPU busy, we can keep it busy with, say, 8, and running very close to peak efficiency. Now, the big limitation of persistent RNNs is that we need to fit the entire weight matrix on chip in the register file. And so on Pascal, it was about a 6 megabyte register file on, on Maxwell is about a 6 megabyte register file. On Pascal, you just saw it was 14. So that's a big leap that's going to help us. But the thing that's even more exciting to me is that NVLink is going to allow us to use model parallelism as well. So we can take that matrix and partition it across the register files of multiple GPUs and use the synchronization capabilities that NVLink provides in order to very efficiently communicate between those GPUs and train our model. So when we combine this style of model parallelism with persistent RNNs with data parallelism, since we need fewer examples per model to keep the GPUs full, we can actually use more copies of the model and use wider data parallelism. That's going to combine to allow us to scale to even more processors. And I think we're going to be able to go quite a bit larger than we've ever been able to in the past, like 30x bigger. I also wanted to point out that my colleague Greg Diamos, who's been doing most of the work on persistent RNNs, is going to be presenting on Thursday. So if you're interested in learning more about this topic, I'd recommend going to see his talk. But just to summarize, we're really excited about the possibilities that NVLink and Pascal give us to strong scale our RNN training. We think it's going to make huge progress in our AI applications that rely on RNNs because we'll be able to churn through far more data far more rapidly.
That's really awesome. Thank you very much. Bryan, you should be a professor.
Thanks.
30 times bigger model. 30 times bigger model. That's the benefit of Pascal and the benefit of the new architecture in NVLink. The next speaker has made a contribution that is just absolutely gigantic. Absolutely gigantic. You know, one of the things I mentioned earlier, these frameworks, the frameworks, are basically the design tools of modern AI. By encapsulating all of the complexity into a nice and easy to use framework so that anybody can design new networks is really important. But more than that, the folks at Google and TensorFlow, Google TensorFlow, open source TensorFlow. They made one of the most important new tools available to everybody for free. It's completely open. On GitHub, it has the most number of likes of contributors and users than any other open source tool. 20,000 likes. And you know how critical engineers can be. 20,000 likes. This tool is being used far and wide now, TensorFlow. It's completely open sourced. And I really believe that this is going to democratize AI. TensorFlow has the opportunity to move a high quality tool that has been optimized for modern computing environments and making it available for every industry, every developer, every researcher, so that we can accelerate the progress of AI. I first learned about TensorFlow watching a talk by Raja Monga, and I thought we'd invite Raja to come on stage and tell you a little bit about it. Raja, why don't you come up and tell us about your important work? Ladies and gentlemen, Raja Monga.
Thank you, Jensen.
First of all, congratulations on TensorFlow.
Thank you.
My goodness, I mean, you guys literally launched this just several weeks ago, and it's just swept through the industry.
It's been great. The community uptake has been great. Everybody seems to love it, and we're really invested in making sure it continues to be even better.
Mm-hmm. And what is the reason why you guys, well, first of all, you guys developed this tool for your own internal development. And,
That's right.
And the thing that I saw in your presentation, which I thought was really great, is you said that inside Google, in just 1 year's time, and there was a chart that you were showing, was on an exponential growth.
Yep.
Like there's currently some over 1,200 applications, from what I can count, that are now basically AI accelerated, deep learning powered, and just a year ago it was only 400. I mean, TensorFlow must have been a vital part of all of the developers inside Google picking it up.
Right. So the tooling definitely makes it easier. You know, we've invested a lot at Google in tooling to make sure that the developers and the researchers can really take what they want to do and scale it up. And now, you know, it's really expanding to many, many different applications and projects.
Now, for the developers that are currently using TensorFlow, what do they love most about it?
So for a lot of the developers, they really want to express all kinds of new things. If you have researchers who want to try out new ideas, like the RNN stuff that Bryan just talked about, or convolutional nets, or over the last year or two, there's this whole thing about batch normalization. So there are a lot of new techniques around these algorithms that developers want to talk about. And with TensorFlow, we've tried to make that really, really easy and allow them to still scale it up.
And it doesn't matter what data set it is, right? It could be a motor skill data set. I might use it to train a robot.
Exactly.
And so whether it's robot or voice or images or whatever we come up with, it could be seismic data for all we care. I mean, just whatever data that data science would like to use to train a network and apply that network in production, that's what ultimately TensorFlow is for.
That's right.
Yeah. The thing that's really, really cool is you guys open sourced it. And because you open sourced it, it made it possible for our engineers. I mean, if it wasn't because of that open source, it wouldn't have been possible for us to start working on adapting TensorFlow for DGX1 early enough.
Yep.
I mean, that's really such an incredible thing. And as a result, computer designers all over the world can do the same. And so we took your open source TensorFlow, and we have now adapted it to DGX1, and it's running on DGX1. Guys, what am I looking at? Is this one real? Here we go. All right, so can you just maybe give us a quick tour of TensorFlow?
Sure. So on the left, you see it's just the command line running the TensorFlow stuff. And it just shows how quickly the engineers here at NVIDIA have been able to take TensorFlow and, like Jen-Hsun was saying, really adapt it to GGX1 and run this. On the right just shows the training curve. It's showing over time how the loss is going down. And it's actually training really on the DGX1 right now with the same TensorFlow that you might use on your machines.
And so this on the bottom, just for the audience, this is the X and Y axes.
Right. So most of deep learning is about optimization. So if you know mathematics and optimization, you're trying to minimize or maximize some value. In this case, there's a loss that we're trying to minimize. And what you see over time here, and this is running real time, how that loss is actually going down and optimizing. So this happens as you train the loss going down. Basically, the number of errors that you make over time goes down, and so this loss goes down as well.
And so if we have a really fast computer, this loss will go down faster.
Exactly.
And if you have a really slow computer, you can wait days for that loss to come down. I get it. Okay. And so this is really so Roger. So what is your hopes and dreams for TensorFlow? Where do you see it going from here?
So like you said, deep learning is a really big thing. We really believe in it. We really think that is the future, right? It's going to be part of every single thing. With TensorFlow, we've built it really to work with all kinds of devices, just like you've been able to do with DGX1, but also run in not just data centers, but all the way to your phones and embedded devices and all kinds of things. We would love to see the community use it, try it out, and use it in all kinds of different ways, and really push it to new territory, stuff that even we haven't gone to today.
Yeah, the thing that's really quite visionary about TensorFlow and the strategy around TensorFlow is that in our case, I really believe that CUDA, our GPU, has democratized high-performance computing. But what TensorFlow is going to do is you're going to democratize deep learning. And I think that's a huge, huge contribution to humanity and to computer science. I want to congratulate you.
Thank you.
All right, thanks a lot, Roger.
Thank you.